Yes, sir.
Okay. Yes. So okay. So today we'll start with a new concept. Order of A. Order of A mod n, also denoted as order of A mod n. So n becomes a subscript, also notation. So order of A mod n is defined as the smallest positive integer m such that a raised to m is congruent to 1 mod n. Okay. So for example, if we want to check for 2, then 2 raised to 0, and let's say so a is 2 and n is 9, let's say. So what is m? Can find by trial and error first. So 2 raised to 0, let's try. So let's start from m equal to 0. So 2 raised to 0 is 1. It's congruent to 1 mod n. 2 raised to 1 is congruent to 2. Okay, now why 0 is not the answer? Because smallest positive integer, and strictly speaking 0 is not considered as positive. Okay, so whenever we say non-negative integers we include 0. Okay, so I'm directly writing, so this is mod 9. 2 raised to 1 is 2 mod 9. Okay, 2 raised to 2 is 4 mod 9. 2 raised to 3 is 8 mod 9. 2 raised to 4, 7. Okay, 2 raised to 5, 5 mod 9. Finally, 2 raised to 6, which is 64, is congruent to 1 mod 9. So we find that okay, m is equal to 6. M is equal to 6. So 6 is the, you can say that order of 2 mod 9 is 6. Okay. Then if you continue, now why did we say smallest positive integer is because intuitively, like okay, so when I go to 2 raised to 7, so 2 raised to 7 will again be congruent to 2 mod 9. 2 raised to 8 will be congruent to 4 mod 9. 2 raised to 9 will be congruent to 8. 2 raised to 10 will be congruent to 7. Just like so, if you see, and then again 2 raised to 11 will be congruent to 5. 2 raised to 11 will be congruent to 5. 2 raised to 12 will again be congruent to 1. So this is in fact periodic. So once we hit 1, the cycle is over and it repeats again. Okay, again from 1 we go to 2, 2 to 4, 4 to 8, 8 to 7, 7 to 5, 5 to 1. Okay, and the smallest integer where we get a 1, smallest positive integer where we get a 1 is 6. Okay, so now can you think of uh, any example where there can be the case that there is no such m? Is it possible? Is it possible that there is no such m for which this holds? Okay, so basically there will always be some exponent m which is greater than 1, greater than or equal to 1, such that a raised to m will be congruent to 1 mod n. So such an m will always exist. In fact, if you see, okay, a raised to m is congruent to 1 mod n. Okay, so n can be anything. N can be prime, composite, n can be anything. So we can apply Euler's theorem mod n. Okay, a raised to phi n is congruent to 1 mod n, right? This is the Euler's theorem. Therefore, the order order always exists. Okay, order always exists, and if you see, n was 9 here. So phi of 9 is what? Phi of 9 is 6. 1, 2, 4, 5, 7, 8. Okay, so phi of 9 is 6. Verified. Okay, so that was about order. Okay, now there is a theorem which says that, n is a positive integer, a is an integer, and GCD of a and n is equal to 1. Okay, then a raised to m is congruent to 1 mod n. Okay, m is also an integer. A raised to m is congruent to 1 mod n if and only if, or is the same as saying equivalent to. So a raised to m is congruent to 1 mod n is equivalent to saying order of a mod n divides m, divides m. Okay, this is small m. A raised to m is congruent to 1 mod n is equivalent to saying order of a mod n divides m. Okay, and a corollary to this theorem says that if this is a corollary, so p is a prime integer number, p is prime, and a is an integer, a is an integer, and p does not divide a, p does not divide a, then order of a mod p divides p minus 1. Order of a mod p divides p minus 1. And okay, so this is the first part of the corollary. It is just like you know, it is just like the Fermat's theorem and the Euler's theorem. So if this we are saying for p, now if n is any positive integer, n is any positive integer, and a is an integer, same conditions as the theorem. GCD of a and n is 1, then order of a mod n divides phi of n. Okay, so where can we use this fact? So any questions up to this part? Okay, so where can we use this theorem and this corollary basically is, suppose we want to find the order of 3 mod 23. Okay, So one way is to try for the powers of 3, 3 raised to 1, 3 raised to 2, and 3 raised to 3, and so on. Another way is order of, okay, so basically 23 is a prime. So we can apply this part of the corollary and say that order of 3, here A is 3, P is 23, and it divides 22, which is P minus 1. Okay, so now order of, therefore, order of 3 mod 23 can be, what all divides 22? 1, 2, 11, and 22. Okay, so now instead of, so our uh, you know candidates have been shortlisted to just 4 candidate powers. Okay, so you can easily check for 3 raised to 1, which is 3. 3 is congruent to 3 mod 23, not the answer. 3 raised to 2 is 9. 9 mod 23 is congruent to 9 itself. 3 raised to 11. Now 3 raised to 11, is there any shortcut for this? Want to calculate 3 raised to 11 modulo 23. Any shortcut? Question to you. How will you calculate 3 raised to 11 mod 23? 3 raised to 3, 3 raised to 3 times 3 plus. No, it is much simpler. Directly you can apply a theorem. 3 raised to 3 times repeated multiplication you are doing. Okay, but there is something more simpler than that. This will also work, but
So we can double the power of 3.
correct. No, well, okay, complete your statement. Complete your statement.
Sir, if I am getting a remainder like when I'm dividing 2 square with 3, I am getting one remainder, right?
Hmm. So double the
Hello.
power of 3 in the sense, what will you calculate?
I will calculate 3 to the power 22 mod 23.
And what will it be?
1.
Why?
Because of that theorem, because
Yeah,
23 is prime number.
Euler's theorem. Euler,
Yes, yes, Euler
Fermat's
theorem.
theorem, sorry.
Fermat.
Fermat's theorem. Okay, so Mahesh has also answered Fermat's theorem, which is correct. Both of you are correct. Okay. So this is okay. You can use repeated multiplication, but this is the shorter way. Okay. So okay. So I know that 3 raised to 22 is congruent to 1 mod 23 because of the Fermat's theorem. Okay. Therefore, I can say that Okay, even though we don't take square root as such, but I can say that 3 raised to 11 into 3 raised to 11. 3 raised to 11 into 3 raised to 11 is congruent to 1 into 1 mod 23. Therefore, this is congruent to 1. Okay, you can also use repeated multiplication any which way. So finally, this is our answer. Order of 3, order of 3 mod 23 is equal to 11. Okay, now okay, now instead of 3, okay, so if the condition is this, if order of G mod P instead of divides P is equal to P minus 1, then we say that G is the primitive root. G is the primitive root or P. For example, order of 2 mod 5. Order of 2 mod 5. What is the order 2 mod 5? Find it.
Hello, sir.
Yes.
Sir, can you explain the order of notation? I'm having a hard time
Okay.
grasping it.
Okay. I'll repeat it. So, order of A mod n means that you will try to find the power of A. Try to find the power of A, okay, such that when you divide that power of A by n, the remainder is 1. Okay, you try to find the power of A such that when you divide that power of A by n, the remainder is 1. That we write as order of A mod n. Okay, now we go for the smallest power. M is basically the power. Okay, so we go for the smallest power such that A raised to m when divided by n gives the remainder 1. Okay, so smallest positive integer m such that A raised to m is congruent to 1 mod n. Then we write that order of A mod n is equal to m. Okay, is it clear now?
Yes, sir.
So in this case, order of 2 mod 5. So which is the least power of 2 such that when it is divided by 5, the remainder is 1. So 2 raised to 0, we don't count, we start from 1. 2 raised to 1 is 2. 2 raised to 1, 2 raised to 1 is 2. 2 mod 5 is 2. 2 raised to 2 is 4. 4 mod 5 is 4. 2 raised to 3 is 8. 8 mod 5 is 3. 2 raised to 4 is 16. 16 mod 5 is 1. So order of 2 mod 5 is equal to 4 because 2 raised to 4 is 16 and 16 mod 5 is 1. Okay, and we tried from the lowest powers, that is 1 2 3, and we found that it holds true for 4. Now in this case our P was 5 and here we are getting the RHS as P minus 1 equal to 4. Therefore we can say that 2 is the primitive root for 5. 2 is the primitive root for 5. Okay, then another example, let's go further. Okay, so order of 2 mod 7 is what? So you'll find the power of 2 such that when it is divided by 7, the remainder is 1. Three is the correct answer. We want the smallest one. So 8 divided by 7 is, remainder is 1. So 3 is the power. 2 raised to 3 is 8. 8 divided by 7, remainder is 1. But as you can see, this is 3 is not equal to P minus 1. P is 7 here. P is 7 and 3 is not equal to P minus 1. Therefore, 2 is not the primitive root for 7. Okay. So this is the concept of primitive root. Okay. Now what happens for a primitive root is, there is an observation. So 2 raised to 0 is congruent to, if we consider all powers of 2 mod 5, because we know that 2 is the primitive root for 5. So if we consider all powers of 2 mod 5, so 2 raised to 0 is congruent to 1. Again, the cyclic nature that I said before, but note that specifically 2 raised to 3 okay. Now from here on it will repeat again, so I'll not write it here. But if you see 1 2 3 4, okay, all the positive numbers, positive integers less than 5, we could find them here. Whereas the same thing, if we consider for powers of 2 modulo 7, where 7, where we know that 2 is not a primitive root for 7. So for 2 raised to 0, 2 raised to 1, right here sideways, raised to 2, 1, and from here it will again repeat itself. So 2 raised to 4 will again be congruent to 2 and so on. So as you can see, only 1, 2 and 4 were generated. Okay. So okay, I'll just introduce a concept. It's not there exactly in your syllabus, but consider any set. Okay, and let's say the set is 1, 2, 3, 4 is the set, and the operation, we are defining a group such that this is the set, and operation is multiplication modulo 5. Multiplication modulo 5. Okay, now you can try this because this is, I'll not go into details of this, but if you see, you can try with, so what you have to do is pick any element such that when repeatedly operated with itself, you can say repeatedly operated with itself generates all other elements. Or pick is not the right word. Actually, we have to find, because this property is not true for all the elements. So find, not any actually. So find an element from this such that when repeatedly operated with itself, it generates all other elements basically. So in this case, 2 is that element, and if we repeatedly operate 2 with itself, so this gives us 4. Repeatedly operated means, so this is once. If we repeatedly operate it twice, it will give us 3. Like, you know, you get the point. So now we are doing it one more time. It will give us, we're going to do is 4. This will give us 1. Operate it 5 times. It will give us 2. Okay. You can simplify, you can verify this. But such an element is called as the generator of the group. Okay. So such an element is called as generator of the group, and the group itself, when this property holds true, that one element of the group can generate all other elements of the group, then such a group is called a cyclic group. A cyclic group, and in this case 2 is the generator. Okay, so 2 can generate all other elements. Okay. So this set also you can say that it is the set Z5 minus 0. The set Z5 minus the element 0. Okay, and this property holds true for this property holds true because you can say that 2 is the primitive root for 5. That's why 2 is also the generator for Z5 and multiplication. Okay. Okay, sir, but for order of 2 mod 7, if we take 2 raised to 6, then it is satisfying the condition. Do we have to take the first one only? Yes, we have to take the smallest one. Okay, fine, fine. Okay, so you communicated amongst yourself and got it. Okay. So got this point, generator, cyclic group, and okay, whatever I said. Any questions up to this point? Property name? No, property name is not cyclic. This is the group. Group is Z5 minus 0 and operation is multiplication modulo 5. Okay. The property you can call it as cyclicity. Like, okay, the group is cyclic. You can say, yes, cyclic group, and the generator is 2. Okay. So next is, okay, so see this fact now. So let P be a prime. Okay. Assume that GCD of G and P is 1. You know, for the example that we saw, this property already holds. Okay. So 2 and uh, 2 and 5, 2 and 7, their GCD is 1. Okay. Now these statements are all equivalent. These statements are equivalent. Okay. This is like saying the same thing in different ways. So first is that G is a primitive root for P. G is a primitive root for P, that is order of G mod P is equal to P minus 1. And now see this statement carefully. Every integer that is not a multiple of P, every integer that is not a multiple of P is congruent to is congruent to a power, is congruent to some power of, I mean to say, okay, some power of g, some power of g mod p. Okay, so every integer that is not a multiple of p, that is, if we take, for example, 2 and 5, then every integer except 10, 15, 20, and so on, multiples of 5, except the multiples of 5, is congruent to some power of 2 mod 5. Okay, what is the meaning of primitive root? Divides p minus 1. No, I did not understand. Divides p minus 1. Abhijit.
Sir, you wrote order of G modulo P is equals to P minus 1.
Yes. Yeah. Yeah. Because G is a primitive root. And GCD of G and P is 1. In see, okay,
Okay, sir. Okay, got.
right, got it. So in general, we can say that, okay, that is what was the definition of the primitive root. That is the next question. Na? What is the meaning of primitive root? Mahesh is asking. So primitive root is actually, it basically it comes from the group theory actually. So, and where it is actually, it is used in the Diffie-Hellman algorithm. We choose a we apply this, but I'll not go into the security algorithms right now. What is the meaning of primitive root? When can we say that a root is primitive? This is not your ordinary root as such. The, you know, the power wala root, that is not the same as this root. This is a very basic, this is what it is defined as. That is what I can say. So up till this point, we had order. Okay. So order of G mod P. So instead of G, like for A, what we had was order of A mod P divides P minus 1. Divides P minus 1, and then divides P minus 1 means it can be P minus 1, it can be equal to P minus 1, or it can be one of the factors of P minus 1 in the previous case, right? Just as in this case, P minus 1 was 22. So the candidate, one of the candidate was 22. And indeed, 3 raised to 22 is also congruent to 1, mod 23. But we cannot say that 22 is the order. Okay. It is the lowest power. It is the lowest power for which when you take the modulus, the remainder is 1. So 22 is not the lowest power, 11 was the lowest power. In this case, what happened is, because the modulus is prime, and it is, so modulus is 7. Let's say modulus is okay. So then we saw two cases. Okay, 2 is also prime, but that is just a we can also check for 3 if you or any other number. Um, let's say we can check for 4 and 5 as well. Okay, this may not be prime. G may or may not be prime. That is not important. What is important is the modulus. If the modulus is prime, then the order will be okay. There is a slight problem of if then. If the order of G modulo P is P minus 1, then G is the primitive root for P. And if order of G modulo P is not equal to P minus 1, and in fact it is something less than P minus 1, then it is just an order. Then it is not a primitive root. And I suggest that, okay, Mahesh, Yash, and Chintamani, if you want to unmute and ask, you can ask it, because did my explanation help, or do you want to ask something else? You can unmute and ask if you want to ask, like if my explanation did not clarify your question.
Sir, so if this condition satisfies, then and then only P is considered, like G is considered primitive root, correct?
Yes.
Okay, and other condition which we have written upwards, like totient of n, such that totient of n.
Okay.
Yeah, yeah. Here, the column. Yeah,
Yes.
yeah. So what is like order of n n subscript a, like it is equivalent to totient of n, or what exactly?
N subscript n. This is the order of A modulo
Huh. Modulo n.
n.
Okay, yeah.
Okay, it divides quotient of n. This means that either it will be equal to n, or it will be one of the factors of n. Like
Okay,
not the factors. So this is the theorem. Like, okay, this is what the theorem says.
okay.
What is the doubt in this? Like, okay, so
No, just like how it is considered as primitive root. Like, what is the significance of that? Like,
well, in this case, this cannot be a primitive. If n is prime, then pi of n will become n minus 1.
okay,
Okay, and if n is composite, then it will be less than that. Any anything less than n minus 1, because there will be some factors if n is composite. Okay,
okay,
so this gives us candidates which can be the candidate powers of A, for which when they are divided by n, the remainder is 1. This gives us the candidates.
okay. We are just narrowing down the multiples like that.
Yes,
Factors. Okay.
yes.
Hmm. Got it. Got it.
Okay.
Yeah.
Anyone else has any doubt? Okay, so I'll proceed. Likewise, there are many theorems, but from cryptography point of view, let's get on to the next problem, that is, maybe I'll not be able to cover the entire thing in today's lecture, so I'll just introduce it with an example, then we'll stop. Okay, so Now this is becoming just plain mathematics. Let me just give you a context. So primitive root is used in Diffie-Hellman algorithm. Have you heard of Diffie-Hellman algorithm? Key exchange. It is a key exchange algorithm. Okay. I don't know. Well, you didn't have it in your. Okay. So what happens is the two parties A and B have two numbers. Say, let's say there is a sender S and receiver R. Uh, they want to share a key. They want to share a key. Okay. So they have to choose. First of all, they choose a modulus. No, not public key, private key exactly. This is used when uh, this is normally used in symmetric key. Like both of them have to know the same key. Whereas in public key, private key, there are two different keys. In this case, S and R must know a shared secret, shared key. So the modulus is decided. Modulus is a prime number, P. And now what they will do is okay, so S will select a number on its own and R will select a number. Okay, but the thing is they have to raise it to a base. So that base is selected as G. Okay, that base is selected as G, and then S selects a number G raised to S mod P and sends it to R. Okay, then R does G raised to R mod P and sends it to S. Now both of them again raise whatever they received from the other party with their own power. Okay, so this was G raised to R received from here, and the number for S is S itself. So S raises whatever he received from R with S, and R raises whatever he received from S with R modulo P. Now this is the shared secret that both of them have. Okay. Now why is it secure and why does it work? I will have to go into the cryptanalysis. Like on the I'll have to take a hypothesis in which there is an attacker, and let's say the attacker does not know S or R. I'll just state this point. So this becomes the shared secret. G raised to SR mod P is the shared secret. Is it clear? Up to this part, is it clear? Yes. This is the shared secret. Now, if the attacker, yes,
Yes, sir. Sir, what is the shared secret?
shared secret is G raised to RS mod P. This is the shared secret.
Okay, sir.
Okay.
Okay.
Now, what if the attacker intercepts one of the messages? Okay. So the attacker will know G raised to S mod P. Let's say attacker intercepts G raised to S mod P. This is S not 5. Okay, this is S. G raised to S mod P. The key here is, and also let's say the attacker knows G raised to R mod P. But the attacker cannot still find out S and R. Okay, so the question to you, like, if I have g raised to s, a number, okay, and okay, I cannot ask you in that way. Okay, I'll just tell it. So if the attacker wants to find s, and by any chance, okay, even if the attacker, so first of all, see, these are only small numbers that we're dealing with for our learning purpose. Okay, so normally p is a very large prime number. Okay, and for that, first of all, the attacker will have to find a generator. Even if the attacker finds a generator, the attacker will have to find a logarithm. Attacker will have to find a logarithm of g raised to s mod p to find s or r basically. So first is he'll have to find g. Second is he'll have to take logarithm to find s, and this logarithm is called as discrete logarithm. Okay. Now this is not a simple problem. If you take for smaller numbers, it is simple to find the logarithm. But if you do that for larger numbers, okay, so for example, if I say 2 raised to x is equal to 32, then you can either know it by memory, or you can solve it like, I'll try for 2 raised to 2, 3, 4, and 2 raised to 5 is 32. Okay, so this you are effectively finding the log of 32 to the base 2, which is 5. It is a solution. Okay, but as the numbers become larger and larger, it becomes difficult to find a log. Okay, so that is what makes the algorithm secure. Okay, now discrete logarithm is yet another concept. Discrete logarithm means that 2 raised to x is 140. Now 140 is not a power of 2. 140 is not a power of 2. Okay, yet you will have to find, like, x will not be an integer, all right, but x will be a real number. Okay, now you know that 2 raised to, so you can find, so what are the limits for x? Just tell me. Limits for x, like, it is between two integers. Between which two integers will x be? 7 and 8, correct? 2 raised to 7 is 128, and 2 raised to 8 is 256. So it is between 7 and 8. Then uh, maybe we can, so there are some techniques by which you can, without any calculator, because again that it is not possible for the larger numbers that will deal with in cryptographic applications to find the log on the calculator. So in this case, you can directly go to the calculator and find ln of not ln, lg of log to the base 2 of 140, and it will be something between 7 and 8. Okay, now in this case, okay, so let me define something. So what is the discrete logarithm problem? Discrete log problem, and we'll see the approaches to solve this problem in the next lecture, but I'll just define the problem. The problem is that given a prime p, a primitive root g, and h. What is h? H is the value of g raised to x mod p. H is the value of g raised to x mod p. It can be g raised to s mod p, g raised to r mod p, you know. It can be g raised to x mod p. It is h. Okay. You have to find x. You have to find x, which is the discrete log of h. You have to find x, which is the discrete log of h. Is the problem clear? This is the problem statement. This is what we want to find. Is it clear? Any questions? Is h the GCD? No. Why did you think? H is not the GCD. H is this. As I said, no, the attacker could listen on the communication and could snoop and understand that, understand one of these messages, that is g raised to s mod p. Attacker will know p, the modulus, and attacker can find out the primitive root. So attacker can find g. Now the attacker knows g and p. The h is this product. H is this product. G raised to s mod p is h. And given that the attacker knows p, g, and h, attacker will have to find the exponent by taking the logarithm. Okay? H is not the GCD. Okay, any questions? Is it clear? Aditya? Yes? Okay. Okay, then if there are no questions, I'll end the lecture here. Thank you.